Welcome to hypothesis testing, arguably the coolest section that we're going to talk about in this class. And so, not going to start with anything too formal. Let's just go through an introduction together. Let's go through some conceptual things together and going to slyly introduce the idea of hypothesis testing. So, let's pretend that we're flipping a coin 50 times. And 75% of these are heads. And now I know, yes, it's impossible to get exactly 75%, but let's just pretend, okay? Flipping a coin and we get about 3/4 of them heads. Is this enough evidence for us to confirm, or at least suspect heavily with statistical backing, that this coin is not fair? All right. So one of the ways that we can kind of approach this is we can kind of visualize this a little bit with a tool that we've used earlier with sampling distributions, right? If we're flipping a coin, there's about if it's fair, October. She is being a very bad girl today. If we're flipping a coin, right, there's a 50% chance that it's going to be heads if it's a fair coin, right? And so if we're doing it 50 times, every time we flip a coin 50 times, that's going to have a random outcome. This is like a sampling distribution, okay? So let's look at this. Let's simulate this. I flipped a coin 50 times. All right, in this case, 58% of them were heads. Did it again, 48% were heads. Do it 10 times. Remember, we use this to show sampling distributions for proportions. If I flipped 50 coins, did this experiment over 1,000 times? Of course, on average, about 50% of them would be heads. The most, after 1,000 times, the most that it was even possible that we ever get after doing this experiment 1,000 times was 70%. It seems really unlikely that we could have gotten 75% heads doing this once. We didn't even get 75% heads doing it 1,000 times. All right, in this little simulation. That's one way to kind of visualize this, tying this into when we were looking at sampling distributions for proportions. All right, so the assumption, right? The assumption is that we should get about 25 heads, right? We should get about 50%, right? 25 heads, if it's a fair coin, right? We're assuming that the coin is fair, but we did this little test and now it's looking, maybe it's not fair. So that's our assumption. We should get about 50% heads. What we want to prove is that we want to prove the coin is unfair. And prove the coin is unfair, that the probability of heads is more than 50%. All right. Now, a coin can be unfair in both directions, but we're specifically suspecting, right, that a coin is not going to be fair in both. A coin could be fair and unfair in either direction. I don't think it's possible for a coin to be unfair in both directions, right? It has to either have more heads or more tails. It can't have more of both. That'd be kind of silly. Anyway, yeah, so that's that. How would a fair coin flipped 50 times behave? On average, there'd be 25. But we know even more than that, right? So we have this from above. On average, a fair coin would be 25 heads. But at this point in statistics, we know a lot. Assume that the population proportion is 50% heads. Then we are taking a sample of size 50. This is, how would it behave? Well, as long as we can satisfy the central limit theorem properties, we could check that. We could say that this p hat is normally distributed. How do we set up a sampling distribution for a proportion? It's normally distributed with mean p. We don't know P, but we're assuming that true population of heads is 0.5. And then standard error, what's the standard deviation of a sampling distribution for proportions? Look at the standard error. And we're going to say that's about the square root of P hat, or of PQ. P hat, no, we'll use PQ over N. All right, so the standard error is going to be the square root of probability of a heads times probability of a tails over how many times we're doing this. What does that equal to approximately? Square root, oh my word. Square root of 0.5 times 0.5 divided by 50. And that's going to be October, don't you dare do that. About 0.0707. 1 second. So we know that P hat, this sampling distribution, this sample proportion, is normally distributed. And on average, as long as this coin is fair, on average, 50% of them will be heads. Oops, I wrote this out wrong. On average, 50% will be heads. And what's the standard deviation? About 7%. So usually it'll be 50%, plus or minus 7%. Again, we know that about 68% of the data for a normally distributed variable is within 1 standard deviation of the mean. About 95% is within 2 standard deviations of the mean, and so on. Connecting the dots, sampling distributions, normal models, the empirical rule, all that stuff. This is how we know that flipping a coin 50 times is going to behave, approximately. So where does our situation land in comparison? Does it have a high or a low probability of occurring? If every time we flip a coin, we do this experiment, every time we do this experiment of flipping a coin 50 times, it follows these rules. It's normally distributed. It'll average to be about 50% if the coin is actually fair. And the standard deviation is about 7%. We did 75%. How many standard deviations above the mean is 75%? Well, calculating how many standard deviations away we are, that's finding a z value, right? So z, remember, is going to be our situation minus the actual population, which we don't know here, we're assuming, divided by the standard deviation. That's how we find a z value for any normal distribution. So specifically for this normal distribution, we're going to find a z value this way. And again, we technically don't know p. We're assuming that the probability of a heads is half. All right, so we're curious about 0.75 minus 0.5 divided by sigma, which is about 0.0707. Type this into a calculator and we'll see how many standard deviations above the mean we are. So it's going to be RP minus the assumed P divided by the standard deviation. We're 3.54 standard deviations away from the mean. That's what Z means. Z is the standard normal. Z has to do with the standard normal distribution. And anytime you see a Z value, that means how many standard deviations above, if it's positive, or below the mean we are. So 99%, 99.7% of data is within 3 standard deviations of the mean. So we're 3.5 standard deviations of the mean. What's the probability of this happening? What's the probability of this happening? Well, we can calculate it. the probability that a standard normal variable or any normal variable is 3.5 standard deviations above the mean, you calculate that with GeoGebra or some other method. There's a lot of methods of doing this, but we have been doing it in GeoGebra. Standard normal, probability that we're bigger than 3.54 standard deviation. Oh, that's a small probability. That's the probability that we're to the left of this little triangle. Sorry. The probability that we're to the right of this little triangle, it's almost nothing. 0.02%. What does this mean? This means that if this coin is fair, it's possible to get 75% heads. But the probability of getting at least 75% heads, not even just exactly 75%, the probability of getting something this unlikely, assuming the coin is fair, is 0.02%. So as a statistician, you can be very skeptical of this little coin, okay? Your friend is giving you this coin and your friend is saying this is fair. You crunch some numbers and you say, well, I did this experiment. Well, looking at the sampling distribution, the probability that something this crazy could happen would be 0.02%. This coin's not fair, and you should not trust your friend very much, all right? Lay out the knowledge, okay? So the probability is indeed small, all right? Sometimes the probability might not be small. Maybe we calculated and we're only 1 standard deviation of the way from the mean, and we'll say, yeah, maybe we just got unlucky, all right? So these are two kind of outcomes. This is our outcome here. And now what we did is basically hypothesis testing. We're going to say this is so unlikely given a fair coin, we have reason to believe it is not fair. Again, it's possible that we're wrong. It's possible it was a fair coin and we're just blaming our friend for nothing. But statistically speaking, this coin is not fair. This coin is rigged. All right, this is hypothesis testing. This is what we did, right? We had an assumption. We had something we wanted to test. We looked at the sampling distribution to say, we have a sample. Our sample is, we flip this coin 50 times. We have a sample. Let's look at the sampling distribution to see how likely or unlikely this was, given our assumption. Well, if it's really unlikely given our assumption, then the assumption might be wrong. And that's what we're doing. And we're looking at sampling distributions in order to do this. Okay? That's what hypothesis testing is all about. In the next couple of videos, we're going to introduce every formal step of hypothesis testing to do it really, really good. Really, really good. That's my mathematician language. And here are the steps. So we're going to set up the null and alternative hypotheses. In our situation, and again, we'll introduce all of these terms later. In our situation, the null hypothesis was that the probability is 50%. This is how we write null hypothesis. We'll introduce that in the next video. And alternative hypothesis, this is what we were trying to prove, was that the probability of a head was bigger than 50%. Okay? And then we're going to need to check the central limit theorem. And this is in order to use sampling distributions. We didn't check this in this video. We weren't formally doing a hypothesis test. And again, sometimes this is going to be for proportions. Remember back to unit 6. Sometimes for proportions, that'll be one set of checks. And sometimes for means, that'll be a different set. In the homework, it's fully focused on proportions. All right. But there are other situations where means will pop up as well. right? Build sampling distribution and calculate test statistic. We did that, right? We said that p hat was normally distributed with mean 0.5 and standard deviation 0.0707. On average, this proportion is going to be 50% heads plus or minus 7%. All right, and we found our test statistic to be 3.54 standard deviations above the mean. Calculate the, and again, I'm going through these. This is an introduction. You don't have to know all of these. We're talking about these, all of these steps in depth in the next video. This is just kind of giving you a little, hey, this is what we're kind of been doing. This is the language that we're going to be using. This is how it all ties in to the future videos. So don't freak out about these steps right now. You can copy it down in your notes and then connect the dots as we continue in the future videos. And then we calculated the p-value, which is really just what is the probability the standard normal variable is bigger than our test statistic. Okay. And sometimes it's bigger, sometimes it's less than, sometimes it's something else that when there's two tails. And we found that this was 0.02%, which we said was very, very unlikely. P-value is going to turn out to just mean, what's the probability that something this unlikely could happen by chance, given our assumption, our null hypothesis that the coin is fair in this example. And write our conclusion. Our conclusion was, this was so unlikely, right? 0.02%, which makes us think the coin is not fair. So these are the 5 steps we're going to introduce in the future videos. These are the 5 steps for hypothesis testing. We've basically introduced them in this video and the logic for how we approach this problem in this introductory video. If you have questions, feel free to ask. And things might not be clear yet, but hopefully, and again, it might even be helpful watching this video at the end as well. Once we've formally introduced all the hypothesis testing, maybe watching this video again to see, oh, how it all ties together. These formal steps that we're doing have logical connections that we showed in this video. All right. Best of luck and have a great one.